Pythagoras theorem that for any right triangle of hypotenuse C and legs A and B, that the square of the hypotenuse is the sum of the square of the legs has been extremely well established for well over 2,000 years, going back to the early Greeks. The usual proof of this involves some geometric shapes and adding and subtracting of areas and other postulates of geometry. There does exist a much simpler proof that can be established entirely by dimensional analysis. The advantage of dimensional analysis proof is the simplicity and elegance of it. The disadvantage of it is that not everyone believes it. Especially students tend to be a little skeptical and unconvinced. The proof is as follows. If you have a length, which we would call the hypotenuse, and it has an angle at each extremity, say alpha 1 and alpha 2, then there is only one right triangle that can be completed from these three items. These three items are sufficient to designate any right triangle uniquely. If you know the length of the hypotenuse and the two angles at the extremities, then the right triangle is uniquely determined. There is only one triangle that can be specified from those three numbers. Therefore, since the triangle is uniquely determined by those three numbers, any property of the triangle can be expressed only using those three properties. And in particular, the area then must only be a function of the hypotenuse and the two angles. The area, however, is a length squared. Of these two parameters, the only one that has a length is a hypotenuse. Therefore, in order for the dimensions of the area to agree with the dimensions of the function, the hypotenuse must enter as a square. Therefore, the area is equal to the hypotenuse squared times some remaining function of the two angles. This would be true for any right triangle. Now we can use this to establish Pythagoras theorem as follows. If we take any right triangle of hypotenuse C and extreme angles alpha 1 and alpha 2, and legs A and B, then the area of this triangle is equal to C squared times some function of the angles alpha 1 and alpha 2. The function is undetermined, and as we see, we don't actually need to determine it. You could determine it with a little bit of simple trigonometry, but it's not important. The important thing is that it will not be present in the final result. The next that we do is take the same triangle and we drop a perpendicular from the right angle to the hypotenuse. This introduces two small triangles. Call them A1 and A2. If you examine A1, then you notice that this angle being alpha 1, alpha 2 is the complement of alpha 1. This angle is the complement of alpha 1. Therefore, it is alpha 2. So these two angles are alpha 1 and alpha 2. So this triangle is similar to the large angle. And quite analogously, the other inner triangle, let's draw it right here, A2, has a side B, a right angle, and this is the angle alpha 2. This angle is complement of alpha 2. This angle is complement of alpha 2. This angle, therefore, is also alpha 1. So these three triangles on the board are similar. Therefore, the area of this triangle, A1, is going to be the length of the hypotenuse squared times some function of the two angles. Now, since the triangle scales up to the original triangle and is completely equal to it in similarity, and the two angles are exactly the same, then the function of alpha 1 and alpha 2 in this triangle is indistinguishable from the function of alpha 1 and alpha 2 in this triangle. And quite similarly, for this triangle A2, then the area A2 is equal to its hypotenuse squared, b squared, times the same function of alpha 1 and alpha 2. Now I'd like to establish the following point in the argument. The original area A is equal to the sum of the areas A1 and A2. This is a statement of the fact that the whole is equal to the sum of its parts. This might be the one weak part in the argument. If you can dispute that, which I think has never been successfully defended, it's just sort of something that we all agree has to be logically. It goes back to Aristotle, that the whole is equal to the sum of its parts. Then the original area is equal to A1 plus A2. However, the original area is c squared times f of alpha 1, alpha 2, and A1 is indeed a squared times f of alpha 1 and alpha 2, and indeed A2 is b squared times f of alpha 1, alpha 2. Notice, as promised, that the function occurs in all three terms in identical fashion and is therefore immediately cancelable out, and so that we have the final result that c squared is equal to a squared plus b squared. Pythagoras Theorem established by nothing except dimensional analysis in the original triangle. This proof is untold number of years old, I'm quite sure. I first came across it in the hallways of the Department of Mathematics at the University of Singapore 10 years ago. It goes back much more than that, I'm sure, to untold author origins sometime in antiquity. So c squared equals a squared plus b squared entirely by simple dimensional analysis. It should be pointed out that there are a couple of simplifications that can be made on that. First, that if you have the length of a line and any one angle, if this is the hypotenuse, then the other angle is automatically determined to be the complement, so that these two items, not the original three, are sufficient to establish the same result. The next simplicity is attributed to Einstein, and it was done in a typical Einsteinian fashion, no pencils at all involved, and it is as follows, that for any similar triangles, the areas of the triangles are in the ratio of the squares of corresponding sides. And that's also simply easily provable with a little trigonometry. So for any similar triangles, the areas are in the same ratio of the squares of corresponding sides. Since the original triangle can be decomposed into two triangles, all three of which are similar, and the original area is equal to the sum of the two smaller areas, then you immediately also establish that the area of all three has to be in proportion to the squares of corresponding sides, and Pythagoras' theorem immediately drops out. Of course, Einstein does not need to use any board work. He simply needs to say a few sentences and gets the idea across. That does bring to mind that there are many Einstein stories in existence, one of which I read and was particularly identifiable with, since I would think I read it during my graduate years. In the 1930s, Einstein left his homeland of Germany because of the political situation and came to the US and was awarded a professorship immediately at Princeton University, where he proceeded to continue his research. He was not noted to the same degree of excellence for his teaching as for his research. In fact, his teaching abilities were not much discussed, let us say that. Nevertheless, Princeton University assigned him a class of advanced graduate students for a fairly difficult subject. At least it was difficult for the students. and Einstein wandered into class the first day, which of course was full of students who came because of his reputation. And he had the book with him, and he opened the book to the day's lessons, took a glance at it, and asked the full room of students if there were any questions. And the students were so in awe of Einstein that every one of them was dumbstruck and could not speak a single word, just sort of shaking just to be in the same room with this particular individual, and could not utter a question. So he dismissed the class. The next class he started the same way, by opening the book, glancing at the problems, and asking if there were any questions. And the students continued, even though they had many questions, because the problems were very, very difficult, continued to be able to open their mouths and to even get out a single syllable, as I'm now having the same trouble. The course proceeded through the weeks with always the same result each day. He asked if there were any questions, and the students could not speak, so there were no questions. Finally, in the week before the end of the course, one of the students realized that the final examination was coming, and he didn't know how to do anything. So he decided to muster up his courage and actually get to see a few problems done. So when Einstein asked if there were any questions, he managed to get his hand up into the air, and Einstein looked startled for a moment, but then said yes. And the student said, could you do problem 31? Einstein said, yes, of course. And he looked down at 31 for a moment or two, and then he looked up at the ceiling for a few seconds with his eyes. Then he turned to the board, and he wrote down a number on the board, apparently the answer to the problem, and he looked directly at the student and said, there, do you see? The student, of course, did not see anything, and so he did not have his knowledge improved at all about how to get a good grade on the final. So he slumped back in his seat for a second or two, but then he regathered his courage, because he really needed to see a solution, and he asked Einstein again. He caught his attention. Einstein looked startled, but called him the student again, and he said, isn't there another way that the problem could be done? And Einstein was a little bit shocked, as if what was wrong with the first way that he had done it. But then he hesitated for a moment. He looked down at the problem again, and he looked up, and then this great glow came over his face, and he looked the student directly in the eye, as admiring him. Of course, as turned to the board and wrote down the same number. And then he looked back to the student and he says, very, very good. End of that. Also end of this little video clip.